Part 2 of how to do experiment with analog electronics. Again, Ohm's Law, and that's an important law in electronics, and it is U is I maal R. Voltage is current multiplied by resistance. We have a resistor here, positive DC voltage. The AC voltage is important to tell that the way a capacitor acts on AC differs because it's frequency dependent. So we only talk now about DC, positive, negative. We have here, say, 12 volts, and that source is able to make 10 ampere maximum output. When we have a resistor here of 12 ohms, the current to the resistor will be, so 12 is puntje puntje multiplied by 12, that's 1 ampere. That means, perhaps this is very basic, and it is too basic, but I want to tell it because it's very important when you study, for instance, a circuit like this that I published today, when the voltage here is 12 volts, and it could be that you want to do an experiment and connect here a resistor of 12 ohms from the positive here to the negative. A current of 1 ampere will flow, and this circuit doesn't use much energy, so all the current and the energy will flow through that resistor, and it will get extremely hot. 12 volt multiplied by 1 ampere is 12 watts, and that's a lot. That's also important when we are talking about doing experiments with analog electronic circuits, but also with digital electronics. The heat development, important, for instance, in a transistor. We take here a normal, more or less normal bipolar transistor, 12 volt, ground plus positive. It's an NPN transistor, so here we have the base, the collector and emitter. Here's the minus. When we set that transistor into conduction by adding a positive voltage here, can easily be done with a resistor of 100k. When that transistor has a certain amplification factor of 50k, 2k, no problem. Current starts to flow, transistor gets into conduction, and the voltage drop here is low. Say it's a silicon transistor, then the voltage drop is approximately 0.8 volts. That means that all the voltage falls over this resistor. And when it's 12 ohms, a current of almost 1 ampere will flow. Important to tell, I don't have a color pencil now, but anyway, flow from here through the collector to the emitter, and the transistor here will dissipate approximately 12 watt. That means that when you have a resistor of 12 ohms here, and take such a resistor in this range, let's take a transistor of 10 ohms. I don't have one at the moment anyway. Take a resistor in this range, in this order of magnitude. Yes, this is in the order of magnitude of 10 ohms, and it is a low power resistor. It will immediately burn out. And that's what I mean when in that first video regard Ohm's law and limit destructive currents. When you use, for instance, in this case, let's keep it simple, a 24 ohm resistor, then we have a current of 0.5 ampere, and 0.5 ampere multiplied by 12 volt is 6 watt. Will still get very warm, but anyway. And when we use, for instance, here, and that's more or less the practical situation, a resistor or a coil, could be a relay coil of 120 ohms. 120 ohms. We have a resistance of 12 is 120, 0.1 ampere. That's 100 milliampere. And that resistor will in general not get very hot. And for instance, you can use this circuit here in a relay application. Instead of that 120 ohm, you can use a relay. Often 12 volt relays are in the range of 220 ohms up to approximately 800 ohms. That means that the current through the relay is not very high. The relay cannot get very hot. That's important. Only say an idea about limiting destructive currents regarding Ohm's law, etc., etc. Let's go to this issue. Use semiconductors that can handle voltage and current. Well, in fact, we have here a good example, because a part of the energy in this circuit will be dissipated inside the transistor. When the transistor has a voltage drop of 0.8 volts, 0.8 volts, let's take 1 volt. To keep it simple, a voltage drop of 1 volt and a current flowing inside the transistor of 1 ampere makes that we have a dissipation inside the transistor of 1 volt multiplied by 1 ampere is 1 watt. That does not seem perhaps much, but I can surely tell that, for instance, the whole bunch of transistors that I have here, they are all small signal transistors, and 1 watt for such a transistor is a lot. It can surely burn out, and you can look for instance to the dimensions of the transistor, how it was made, whether the encapsulation is plastic or metal, etc. When you have a metal part on such a transistor, you can be sure that the conduction of heat to a heat sink will be much more easier. So all these transistors here in this box are in fact not made for to have a dissipation of 1 watt. Too much. But on the other hand, when we have this transistor, for instance, the BD139 and the BD140 are made to dissipate surely 1 watt on a heat sink, and here's that metal plate, you can cool it. Surely they are able to do that, and they can even go to approximately, in theory, 6 watts, but in general I always use them only for 4 watts approximately. Are very good transistors, and important to tell that these transistors, the BD139 and the BD140, can have a higher voltage on their base compared to the voltage between the collector and the emitter. That's a unique property when you study the transistor technology. Anyway, that was Ohm's law, dissipation in the transistor. Of course, perhaps my camera will run out, but anyway, let's look at a bipolar transistor circuit. I know that bipolar transistors are far from ideal when talking about power circuits, but anyway. 11 minutes on my camera, I have some time. Let's say we have here a real power transistor, the 2N3055. We have here, for instance, 30 volts. The source is able, the voltage source is able to give out 5 ampere. The output is able, that's what I mean, it's able to do. Here we have a, say, low resistance source, load is what I mean. We set the transistor into conduction here with a resistor, and we have here, for instance, a Zener diode. It's not the best example, by the way, because the amplification factor of the 2N3055 is not very high, approximately 75 at its maximum, but anyway, 30 volts in. Let's make here a 12 volt Zener. That means that we have here, at this low resistant load, a voltage drop between 30 volts minus 12 volt is 20 volts, 18 volts drop. So here, between these two electrodes of the transistor, the collector and emitter, we have an 18 volts drop. And say the load makes that we have here a current of 1 ampere. That makes that inside the transistor we have a dissipation, a power dissipation of 18 volts multiplied by 1 ampere is 18 watts. That's a lot. This transistor will get very hot. That's important to tell. It needs a heatsink. When the current gets higher than 1 ampere, say it's 2 ampere, then we have 2 multiplied by 18 is 63 watt, and we know that the 2N3055 can only handle approximately 150 watt. It will get quite hot, it surely can handle it, but it needs a heat sink. These are, say, the things to take in account regarding Ohm's law and limit destructive currents. and use semiconductors that can handle the voltage and the current. And I've not talked about the second breakdown effect. That's another issue. Thanks for watching.